The goal of this video is to prove the theorem we left from last video. Basically, we want to show that if we have a pre-measure on an algebra, then we run the Cairo-Theodori theorem and get an outer measure and then a complete measure mu bar. Then all the algebra elements are, first of all, also mu star measurable, and then the mu bar will extend the mu on this algebra. So the proof is divided into two parts. So first of all, let's prove the following claim. Suppose I start with some element from the algebra. I first want to prove that the mu star of A, which is the outer measure, is actually equal to the pre-measure of A. So the outer measure kind of preserves the pre-measure already. All right, so let's prove this fact. So first of all, you may notice by the definition of this mu star of A, let me remind you how it's actually defined. It's defined as the infimum of any mu of the cover of this A. So here the mu of AI, I go from 1 to infinity, where this AI is a cover of A. So A is contained in the union of these AN. All right. So here these AI are coming from these algebra. So this is how we define this outer measure. So and you may notice that A is a cover of itself. Okay, so A certainly contained in A itself. Well, so if I just use the A as a cover of A itself, well then I know the mu star of A being the infimum over all these covers. That would imply the mu star of A should give me a smaller value, so it's at most mu of A, okay? Because mu of A is achieved by the cover A of covering itself. So basically, we just need to prove the other direction. So we want to show the converse, all right? So how do we show that? So now let's take any cover. So let's take any A contained in union of these AN, where each of these AN is inside A. So we want to show that this cover actually will give you a value that's bigger than mu of A. So in other words, mu of A will be the infimum. Okay, so how do we show that? Well, first of all, this union, this infinite countable union is not going to be very nice. It may not be disjoint, okay? So we're only given a pre-measure that behaves pretty well over disjoint union, but we don't like non-disjoint union. So, well, this goes back to our standard trick of making a non-disjoint countable union into a disjoint countable union. So let's recall we can make this potentially non-disjoint countable union as a countable union of some Bn. Okay, so how we did that is that we let B1 is equal to A1, B2 equals to A2, but not in A1. And then the nth one, so B of n, is just equals to everything in An, but not in the first n minus 1 of them. So I go from 1 to n minus 1 of these AI. I take away from AN. So and so on. So now we have a collection of B, and we saw that these B are disjoint, and their union is going to be this union of AN. So they have the same union. Now we have this collection of B. So let's think about what we need to show. Okay. So we need to show the following. So on one side, I want to show that mu of A should be the smallest of among those covers. So it should be the infimum. So I want to say this is less than equals to the summation of a cover. So this is mu of AN. So going from 1 to infinity, I want to show somehow this is smaller than equals to this summation. Now we made this union of AN into a bunch of BNs, and these B are disjoint, but they're not related to A yet. Okay, so how can I relate them to A? Well, how about let's take an intersection, okay? So let's let each Cn to be equals to Bn intersect An. Sorry, all right. All right, so let's let each Cn to be actually the Bn intersect A. And because Bn are disjoint, we know by intersecting this A, they're all disjoint as well. And if you consider the union of the Cn is essentially the union of Bn and intersect A, but union of Bn is equals to the union of An, and then the union of An is a cover of A, so when you intersect A, you will recover A back. So now A is written as a countable disjoint union. So here are all countable. So A is a countable disjoint union of these elements Cn. Well, there's one more thing we need to be careful. I need to show these Cn are actually in the algebra. So what we know is that each of these An is in the algebra. And from the definition of these B, so you see each B is starting from some finite collection of An, and you do some union and you do some set difference. So you can convince yourself each of these Bn is also inside the algebra. And now your A is also inside the algebra. That's where we started. So their intersection Cn is also inside the algebra, okay? So because Cn is in the algebra, now A being an element in algebra is written as a countable union of these C. So we have that mu of A is actually equal to the summation of mu of Cn. That's by the definition of a pre-measure. And now what's our goal? Our goal is to show that it's less than or equals to this summation of mu of An. Well, as you can see, these Bn are contained in An, and Cn is a subset of Bn, so it's certainly contained in An as well. So each of these Cn is contained in An, all right? And because of that, well, you will see that because Cn is a subset, then the mu of An, you can write it as mu of An take away Cn plus mu of Cn. So this is by the finite additivity of a pre-measure. So here An take away Cn is in the algebra. It's destroyed from Cn, and their union give you An back. So from there, we can see that because mu is positive, mu of Cn is less than or equals to mu of An. So this entire thing is less than or equals to the summation of mu of An. All right. So now we show that mu of A is bounded above by the summation. And we know the mu star of A is the infimum of all the summation of mu of An. So by taking the infimum, we know mu of A will be smaller than the infimum of these, which by definition is mu star of A. And we know it's less than or equal to mu of A because A is a cover of itself. So these are all equalities. Okay, so we proved that the mu star of A is actually equals to mu of A. Okay, so this is the first part of the proof. Now the second part, we need to actually show that an algebra element is actually measurable. Okay, so that's second claim. If I have A inside A, then A is measurable, or mu star measurable. So how do we show that? Well, we need to verify the definition. So let's take any set E, okay? So we only need to worry about the case when mu star of E less than infinity, and recall we actually want to, the goal is to show one direction, the non-trivial direction of an inequality we need to show the mu star of E intersect A plus the mu star of E intersect A complement. That's going to be less than equal to mu star of E. Okay, the other direction is given by the subadditivity. Okay, so this is our goal. Okay, let's keep that in mind. All right, so how do we show this? Okay, how do we show this? Well, we need to first have a nice approximation of this mu star of E. Okay, so E is just some set. It doesn't have to come from your algebra. So we need to approximate using the algebra. Okay, so we know the mu star of E by definition is the infimum of a bunch of stuff. So infimum of mu of AI, where I greater than equal to 1, so each AI is in A, and this E is contained in the union of these AI. This is the definition. So because mu star of E is this infimum, we can always pick something that's close enough to this infimum. So let's take every epsilon greater than 0. Then I can find some cover. Let's call it, give it a name. Let's call it, maybe call it En. Okay, and going from 1 to infinity. So here, each En is an algebra element, and E is contained in the union of these En. And what we have this En is a nice approximation of mu star of E. So, well, because it's a cover, it has to be greater than equals to this mu star of E when I sum up all their mu of En. But it's not too bad. So it's less than equal to mu star of E plus an epsilon. Okay, so it's within epsilon of this mu star of E. All right, so now I have this collection of En. So let's look at our goal. Our goal is to evaluate mu star of E intersect A plus the mu star of E intersect A complement. Okay. So because E is contained in these En, so by replacing E by this union of En, I can only increase. So I will have a less than equals to this union of En and replace it. Let's replace E by this union. You can make it increase. Okay, so let's write that down. And you may notice that when you take a union and you intersect this fixed A, essentially you can say, well, let's just take the intersection first and then we do the union. Okay, so you can remove these brackets and make the intersection first. And now what do you have? Well, you have a countable union of stuff, and mu star we know is an outer measure. So by its an outer measure, we know is less than equals to the summation of each of these mu star. Okay, so this is by the sigma subactivity. You get they're less than equals to these summation. All right, so this is sigma subactivity of mu star. Okay, and now let's look at these sums. Okay, so each of these En by definition it come from A, and these A, well, we know A is from A, so A complement is also from A by A is an algebra. So each element is actually from A. So by claim 1, the first claim, we know that the mu star and mu will agree on the algebra A. So here this is actually equal to the following. I replace all the mu star by mu, then I actually get the same thing. So they're all equal. Okay. And now we have two infinite sum. We can make them together. So let's just group them up. Okay, so this is mu of En intersect A plus mu of En intersect A complement. And now you notice one thing, the En intersect A and En intersect A complement, they are actually disjoint, okay? So E intersect A, and if you union the E intersect A complement, Well, basically you're asking everything that's inside E and is either inside A or A complement, and you can convince yourself this is just equals to E, okay, or each of these are En. So we know mu being a pre-measure, we just saw mu is actually finite additive, okay, so here everything is in the algebra. So by the finite additivity of this mu, I got this is mu of their union, which is mu of En. And if you recall, when I choose these ENs, the summation mu of En give me a good approximation of mu star of E. So by good approximation, I mean it's within epsilon of mu star of E. Okay, so now let's see what we proved. Okay, so let's go back. So we start from the left-hand side of our desired inequality. So we start with mu star of E intersect A plus mu star of E intersect A complement. And we prove that it's less than or equals to mu star of E plus some epsilon, where epsilon is arbitrary. Okay, so let's let epsilon goes to 0. We show that basically the mu star of E intersect A plus mu star of E intersect A complement is less than or equals to mu star of E plus any epsilon. So let epsilon goes to 0 is less than or equal to mu star of E. So this shows that A is actually mu star measurable. So another way of saying A is mu star measurable is just say A is inside the sigma algebra of mu star measurable set. So A is in B. Okay. So now to show that the Carathéodory mu bar is actually an extension of this mu. Well, recall the mu bar is basically so mu bar of a set B for any mu star measurable set is simply the mu star of B. Okay, so if I take A inside A, then mu bar of A, because A is actually mu star measurable, so A is actually in B. Okay, so this is actually equals to the mu star of A. And we show the mu star of A is equal to mu of A, so they are the same. Okay, so in other words, mu bar, when I restrict back to this algebra, then we actually recover this mu.